going to talk about a class of oscillators that really leans into nonlinearity. All of the oscillators we've talked about so far have relied on a linear system, or at least a system that's linear for part of its operation, to create a feedback loop with a loop gain of -1. Relaxation oscillators and digital oscillators instead rely on digital systems, which are highly nonlinear by design, to create their oscillations. That's daunting, but digital systems are well enough behaved that we can analyze these circuits. The first oscillator we'll look at is called a Schmidt trigger oscillator, which is part of a family of oscillators called relaxation oscillators. Relaxation oscillators rely on charging and discharging an RC network to set the frequency. Unsurprisingly, Schmidt trigger oscillators depend on a device called a Schmidt trigger, which is a digital gate with a hysteretic transfer function. Hysteresis is a type of memory that means your transfer function depends on past inputs. That sounds complicated, but it's not so bad if we look at an example. I'll fill out the Schmidt trigger transfer function on the axes below. When our input voltage is going from 0 to VCC, we see that our output looks like an inverter transfer function. It's high until we reach some threshold, VHL, and it drops low. One weird detail is that the inverter doesn't transition at VCC over 2 necessarily. It transitions instead at this VHL threshold, which stands for the high to low voltage. As you may have guessed from the arrows in VHL, the behavior of the Schmidt trigger is different when we decrease Vn from VCC to 0. This also looks like an inverter transfer function, but the output rises at a different voltage, VLH, which stands for the low to high voltage. And the fact that there's a difference between VLH and VHL makes this transfer function hysteretic. This kind of shape is called a hysteresis. We can make an oscillator out of this pretty easily by attaching a simple RC network around the inverter. When the output is high, that will charge this cap such that the input climbs up towards VHL. And you can see that here. When the input reaches VHL, the Schmidt output toggles low, and our output starts climbing down towards VLH. When the input reaches VLH, the output toggles to high again, and we start climbing up. Each of these charge or discharge segments is governed by a standard first-order differential equation, so we can quickly write the rising and falling voltages using the sort of initial voltage, the final voltage, and a standard kind of first-order decay. Now if you set V rise equal to VHL, or if you set V fall equal to VLH, then you could invert these equations to calculate the amount of time it takes to rise or the amount of time it takes to fall. And the frequency of oscillation is going to be given by 1 over the sum of 1 rise cycle plus 1 fall cycle. Interestingly, the duty cycle isn't necessarily 50% in this circuit. It's going to be given by the ratio of T rise of which is when VHL is high, which is when the output is high, divided by T fall, which is when the output is low. The most famous way of implementing relaxation oscillators is an integrated circuit from the 1970s called a 555 timer. These are remarkably commercially successful chips. They were released at the same time as the Intel 4004, and they're still on the market. They've become a bit of an obsession in some corners of the electrical engineering community, and you can find recipes to get them to do all sorts of tricks. We'll be focusing on making them into a Schmidt-like relaxation oscillator with a little bit more nice programmability. Before we hook up the relaxation network, let's take a look at the internals of this chip. The 555 timer gets its name from a trio of 5 kilo-ohm resistors that provide some reference voltages to these comparators. That means the upper comparator will put out a digital high voltage when the thresh pin exceeds 2 VCC over 3. And the lower comparator will put out a digital high voltage until trig exceeds 1 VCC over 3. These thresholds can be tuned by putting some resistors in parallel with the 5K network using the cont pin. These two comparators drive an SR latch, and SR latches set their outputs and remember them in response to set and reset inputs. So if the lower comparator sends a pulse in, then the output Q will go high and stay there. If the upper comparator goes high, then the output Q will go low and stay there. Slash Q is the logical complement of Q, so it's high when Q is low and low when Q is high, and it controls this handy BJT that's attached to the discharge pin. This type of pin, by the way, just sees the collector of a BJT, and so it's referred to as an open collector output, which is a common type of interface to chips. We make our oscillator by shorting the thresh and trig pins together in order to sort of be the input to our relaxation oscillator. That's like the input to the Schmitt trigger on the previous page. And just like the previous page, that's hooked to our capacitor, which kind of has the state of our oscillator stored in it. The capacitor is pulled up to VCC through R2 and R1, but we have the discharge pin attached between R1 and R2 here in some type of interesting feedback. So the oscillation comes from charging and discharging this cap, just like a Schmitt trigger oscillator. When Q is high, slash Q will be low, and the discharge BJT will be an open circuit, so that means the cap will start charging up through R1 and R2 to VCC. When the capacitor voltage reaches 2 VCC over 3, however, we will send a high signal to the reset value here. Q will go low, slash Q will go high, and this transistor will start sucking current through the discharge pin off of the capacitor. So the cap will discharge through R2 and the BJT. And then when it discharges down to VCC over 3, we send in a set signal to the SR latch and go back to Q being high. The rise and fall time of this are first order behaviors again. So we're rising from VCC over 3 to higher voltage in kind of a first order way. And we're falling from 2 VCC over 3 down towards 0. It's worth noting that the rise and fall have different time constants though. The rise is governed by R1 plus R2 times C, and the fall is governed by R2 times C, which means this actually can't ever have a duty cycle of 50%. Just like before, you can find T rise and T fall values by substituting thresholds in for V rise and V fall and inverting the equations. Note that the thresholds are going to be VCC over 3 and 2 VCC over 3, which means you can factor VCC out of every term in these expressions. And one neat feature of 555 timers is that their frequency is perfectly stable against changes in VCC, which is really cool. The last type of oscillator we'll talk about is a ring oscillator. Ring oscillators are hugely important calibration tools in digital chips, and they also get used in some clock generation circuits. Understanding a ring oscillator depends on understanding inverters, but we can get away with the most basic model of an inverter, which suggests that an inverter changes its output to the opposite of its input after a small delay. And we can see that illustrated for the leftmost inverter. On node 0, we see that there's a rising edge on time t in, and that results in a falling edge at time t in plus t inv on node 1. And this t inv is called the inverter delay. So this falling edge on node 1 will create a rising edge on node 2, again t inv later, and then t inv after that we'll get a falling edge on node 3, then a rising edge on node 4, and then a falling edge on node 0. So all of these transitions seemed fine, but this falling edge is a little bit troubling, because this whole process was kicked off by a rising edge on node 0. so there seemed to be an apparent contradiction between this and this. However, this falling edge happens 5 t-invs after this rising edge, so there's no reason that we can't have just another falling edge in this shape 5 t-inv later. And if we do that, then that will result in a rising edge here, and a falling edge here, and rising and falling and rising, and cause every node in the circuit to toggle again. And that will continue forever, because an odd number of inversions will never reach a sort of stable equilibrium. So we have kind of a stable oscillation in this digital circuit. The frequency of this oscillation is 1 over 5 times t-inv, but you can make ring oscillators of different frequencies by changing the number of inverters in the ring. Any odd number except for 1 will do. In fact, you can generalize that concept to put other interesting logic gates into a ring oscillator loop. You could argue, in fact, that all these 4 rightmost inverters are doing is creating a delayed copy of the output of the first inverter and sending it back to its input. So you could replace those with AND gates and OR gates and other stuff that let you play some clever tricks with the state of your oscillator and toggling sort of different patterns into and out of it. That's fun, but you might wonder, and if you do that, your total delay is 1 over the delay of this plus the inverter delay, which gives you the frequency of oscillation is the inverse of that. Anyway, that's fun, but you might wonder what's so special about digital delays, and wonder if you could use an analog delay here to get the same effect. The answer is yes, though the math gets harder. You'd analyze that by finding a describing function for the inverter, and then calculating the loop gain for your delay, which would look like some sort of phase shift. So, in summary, relaxation oscillators digitally switch to charge or discharge a capacitor in feedback once the output voltage passes some threshold. In a Schmitt trigger oscillator, the threshold is set by the hysteresis of the Schmitt trigger, and in 555 timers, the threshold is set by this internal 5K, 5K, 5K divider that provides reference voltages to comparators. And the frequency of the oscillation is 1 over the rise time plus the fall time, which are set by sort of simple first-order RC calculations. And ring oscillators are digital oscillators that rely on an odd number of inversions in a loop to force digital gates to switch states forever. And the frequency of oscillation is given by 1 over the size of the loop times the inverter delay.